What we're going to do now is we're going to use that concept of potential energy and kinetic energy, and we're going to start talking about this thing, conservation of energy. It helps us solve an awful lot of problems. And it starts out with this: energy is neither created nor destroyed. So whatever energy there is before has to equal the total after, unless we add energy to the system. How do we add energy to the system? By doing work on the system. If you do positive work on the system, you're going to end up with more energy in the system afterwards. Again, if I have a ball and it's sitting there and it has basically no energy and I push it, I added work to the system, my new energy in the system will be bigger. Usually we talk about that with the work-energy relationship. Work is equal to change in kinetic energy. Because remember, kinetic energy, for what we're talking about in this class, mechanical energy, kinetic and potential are mechanical energies. And kinetic's the only real one. Potential is this relative thing, so it's a little squishy. It's not a real energy. So work would be equal to the change in kinetic energy. But we can take out some of the work that's done by gravity and consider that part of the system. What do I mean by that? When I drop a ball, okay? When I drop a ball, if I'm only looking at the kinetic energy, then the energy of that system is the kinetic energy, okay? But if I start looking at that ball relative to the Earth's gravitational field and I start including the Earth in my system, think of this. I push those two things apart. I'm increasing the energy of the system, and it can snap back, if you think of it, by the ball falling down. So when you're talking about potential energy, we are really talking about the Earth and object as a system. Okay, that's really kind of an important part. System of Earth and object. Okay, if we consider that as a system, then we can start talking about this thing called potential energy. By lifting something, we increase the potential energy of that system. By dropping it, we decrease the potential energy of that system. You can think of these things as being held by a spring, and you're spreading them apart, and then they can come back together. So if we are talking about the system of the Earth and object, then the external work on that, in other words, like if I pull something up, I am increasing that energy. Okay, if I throw something down, if I push hard on something, I'm actually still increasing. I'm doing work on the system. But we're going to consider that Earth object system anytime we're talking about potential energy. And I'm going to be saying that Earth object system very frequently. So let's take a look at that Earth object system and how we use it. So we've done one. I've got a ball here. Let me say I'm going to throw this ball in this direction. It's got a velocity of 20 meters per second. Okay? And it starts out 4 meters above the Earth. And it has a mass of 2 kilograms. I like 2 kilograms. Let me do 0.5. I'm just going to change things a little. M equals 0.5 kilograms. Okay, so let's go through how this whole thing plays out. Now, as I said, whenever I'm talking about potential energy, I'm going to call the potential energy the height. Excuse me. I've got to pick a height at which the potential energy will be 0. And so for me, in this case, I'm going to pick the ground to be 0. Okay, H equals 0, or U, potential energy, is 0. Okay, so when the ball is on the ground, I'm going to say it has 0 potential energy. You could absolutely pick this to be height equals 0, potential energy equals 0, to be your reference location. So I'm going to do two things. I'm going to find out how high it goes, and I'm going to figure out how fast it's going when it comes to the ground. Okay, so what I like to do is I like to kind of draw a picture. It's doing this kind of thing. And I like to label the energies at specific locations, because potential energy depends on location, it depends on position, and really depends on position relative to some reference point. So right there at the very beginning, I've got a potential energy of mgh, mass, times 10. 0.5 times 10 is 5, times h is 4, 20 joules. Okay. It's got a kinetic energy, 1/2 mv squared. Let me write those over here. mgh, 1/2 mv squared. You should be writing the equation and substituting. I don't like to have too much on here because it gets a little busy. 1/2 times m times v squared. That's going to be 400. 400 times 0.5 is 200 times 1/2 is 100. So it has 100 joules of kinetic energy. So my total energy right now is going to be 120 joules if I'm calling this zero potential energy. So it has some potential energy because it's raised up, and it's got kinetic energy because it's moving. Could be moving in any direction. If it's moving this way, that way, that way, that way, that way, at 20 meters per second, it'll still have that same kinetic energy, right? Okay, so I know nothing else is going to be in there. Okay, I'm not going to worry about friction. Nothing else is touching it. So this work is going to end up being 0. So I know the total before has to equal the total after. So now I'm going to go up here and I'm going to say total. I'm going to call that prime. I don't know. I could just call the total at this spot. It has to be 120 joules. There has been no negative work done on it. There's been no positive work on it. The only work done on this is by gravity, but we're representing gravity via potential energy. We don't have to do a work equation for that. So the total energy after is 120 joules. Well, look up here. The velocity at the top is 0. So the kinetic energy is 0. Therefore, 120, we take these two things and we find out that the potential at the top has to be 120 joules. Okay? So we've just shown that we can now use this equals mgh to find the height. And we've just shown that using these two locations and having some information, we have complete description at one position. So we know that total has to be the same there. We know the kinetic up there. We can find the potential. Okay? So that will allow us to solve. And let me just do it. mgh, m is 0.5, g is 10. So we divide this by 0.5 times 10, which is 5. That divided by 5 ends up being, I should be able to do this, 24 meters. Okay, 24 meters. So that's how high it went. Once again, you can do this with force and kinematics, but look at that. That's a really pretty easy way of solving that problem. Okay, now, and let me give a little window so I can see. Now what I'm going to do is do the trip down. And I'm going to find out how fast it's going at the end. Okay, when it hits the ground. So if I do that, I'm going to look right here at that spot. And I know, guess what? Total energy has to be 120 joules. No work has been done on it in the meantime. Okay? But now I know the potential energy is 0 because it's at ground level. Well, if the potential energy is 0, 120 minus 0, 120 joules. The kinetic energy is 120 joules. So 120 joules, just let me write it over here, kinetic is 120 joules equals 1/2 mv squared. 240 equals 0.5 times v squared, divide by 0.5, and you end up with 480 equals v squared. So v is going to be the square root of 480. That's going to end up being 20-something meters per second. Okay? So look what we were able to do. If we have one place, you're always going to know one place where you know everything. You know the total energy. Okay? Then if there's no work done on it by an outside force other than gravity, which is we consider part of the system, then the same total is going to take place anywhere in there. Okay? And the way this form always is going to go is if I said at this location, find the velocity, I would have to know the height. So I'm either going to give you the height, which gives you the potential energy, total's 120, and you can subtract and find the kinetic, or I could give you how fast it's going. That would give you the kinetic energy, 120 minus that would give you the potential. So as long as you're okay with these equations for potential and kinetic, we can always solve these problems and figure out how they work out to give you either a height or a velocity. Okay? Now, let me really quickly look at this. Okay? As this thing slides down the ramp, if I know how its beginning and final height, okay, I can figure out the change in velocity using this exact same approach. And I strongly recommend writing the energies at these locations, because they do have to do it. While it's at this spot, it has a certain potential and kinetic. So if I know its initial height, I know the potential energy. If it started from rest, I know the kinetic energy. Let's see, even if I knew what the velocity is, I know the kinetic energy. When I have those, I can find the total. When I can find the total at one place, I know the total anywhere else. And so all I need to know is either the height or the velocity, and I can find the other one using this conservation of energy. So that's the way standard conservation of energy problems go. Okay. But what we're going to do in the next lesson is we're going to figure out how work adds to this. If you think of this problem, if I throw it up, if there's air resistance, you can think of it as losing a certain amount of energy. It's energy being transferred to another system, the air particles, okay? So the totals won't be the same. The totals will change as this thing goes through the path. So we want to be able to use conservation of energy and then also use this concept of work either adding or subtracting energy so we can find the solutions to the problems.